Welcome back everyone to another video on this channel, HEC Physics. In this video, I'm going to cover the electromagnetism part of 2.6 Electricity and Electromagnetism External Standard. Now, in this standard, in year 12 physics, it's mostly focused on electromagnetism. That means interaction of electricity with magnetism. So we are going to consider situations where we have some form of electricity, for example, current or moving charges, and then we are going to analyze how these interacts with magnetic fields, with some other external magnetic field. Now, overall, there are four main topics that we have to learn in this part of the standard. So, let me quickly summarize what are these four main topics. So, number one is current carrying wire in a magnetic field. And in this part, we are going to look at the interaction of this current carrying wire with an external magnetic field. Okay. Number two is, instead of current carrying wire, what we are going to consider is just a single moving charge. So we will have a charge particle, a single charge particle moving in a magnetic field. And this is another example of electromagnetism. And this part focuses on interaction of this moving charge with an external magnetic field. Okay. Number three is a conductor. So we know what conductors are and how they are different from insulators. So conductor, a single conductor which is moving in a magnetic field. So it's placed and it's moving in an external magnetic field, and that's our third example of electromagnetism. And number four is basically application of some of these effects. So first application we are going to consider is DC motors, which is an application of current carrying wire or interaction of a current carrying wire with a magnetic field. And then another application that we are going to consider or we are going to learn about is generators, which is just opposite of the current carrying of DC motors. And this one is an application of a conductor moving in a magnetic field and how it interacts with this external magnetic field. So these are the four main topics that you will need to learn as part of electromagnetism. So we'll start with the first topic, which is current carrying wire in a magnetic field. Okay, so let's start with a wire which is connected to a power supply, and therefore we have a current I through the wire. Now, it is well known that if we have a current through a conducting wire like this, then it sets up a magnetic field around it. Now, just like a charge particle sets up an electric field, and we can show that electric field by drawing electric field lines around a charge particle, similarly, the magnetic field set up by this current carrying wire can be shown by drawing the magnetic field lines around this wire. Now, these magnetic field lines for a current carrying wire are specifically circular. So, I'm going to draw circular magnetic field lines around this current carrying wire. And because the strength of the magnetic field is large or bigger close to the wire, that's why we have to draw these magnetic field lines more dense close to the wire. And then as we go further away from the wire, we will draw the magnetic field lines more spread out to show that it's less dense, which shows the strength of the magnetic field is less as you go further away from the wire. We have learned this about electric field as well. We know that the density of the field lines shows us the strength of the field. So over here, we applied the same thing. We drew the magnetic field lines more dense close to the wire to show that B is stronger there, and then less dense further away from the wire because B is weaker there. Okay, so this is our external magnetic field. Sorry, this is our the magnetic field set up by this current carrying wire. Now, to get the direction of these circular magnetic field lines, we will have to use right hand grip rule, which you might be familiar with from last year. But what it tells us that we'll have to point the thumb of our right hand in the direction of the current through the wire. And then if we curl the rest of our fingers, then the curling of the fingers shows us the direction of this circular magnetic field lines. So please ignore my drawing. It's not, it's horrible, but you get the idea. So basically, take your right hand, point your thumb in the direction of the current. This is our thumb pointing in the direction of the current. And this is the curling of the finger, which gives you the direction of the circular magnetic fields set up by the current carrying wire. So if we apply that same rule for this current carrying wire over here, then if we point our thumb straight up and then curl the fingers of our right hand, then we can see those are curling in the anti-clockwise direction, and therefore these magnetic field lines are pointing in anti-clockwise direction, these circular magnetic field lines. Okay, so that's how we get the direction of the magnetic field set up by this or by a current carrying wire. Okay. Now, through this drawing, we are basically trying to show a 3D diagram in a 2D surface, which is quite challenging at times. So that's why I want to show you a slightly different representation of this same magnetic field set up by a current carrying wire, which is basically showing the same magnetic field in a 2D surface. So if I take that same wire, so this is our wire here, and then uh, using the right hand grip rule, if we consider the magnetic field on the right hand side of the wire, then we can see that the magnetic field lines are pointing, those circles are basically pointing away from us into the surface, and these magnetic field lines are vectors because they have direction. And if we want to represent a vector which is pointing away from us, then we know we can do it by drawing these magnetic field lines or these vectors as crosses, because a vector pointing away from us is shown as a cross. Okay, and these crosses will be more dense close to the wire, and then as we go further away from the wire, then it's less dense over there. Okay, similarly, on the left hand side of the wire, we will have the magnetic field lines pointing towards us. These circles will be coming out of the surface, and therefore we can represent these vectors, the magnetic field line vectors, as dots on the left hand side of the wire. And same process, the dots are more dense close to the wire, and then as we go further away from the wire, they are more spread out, showing the magnetic field strength is weakening as we are going away from the wire. So this is showing the magnetic field set up by the current carrying wire in a 2D surface. It's a 2D image, basically 2D diagram. Okay, so now what we are going to do is take this current carrying wire and place it in an external magnetic field. So that means we are going to start with a new magnetic field, an external magnetic field. And I'm going to show that magnetic field by crosses. So it's a uniform magnetic field set up by some other magnets, and these magnetic field lines set up by these external magnets, by these other magnets, are pointing uh, into the surface, and therefore I'm drawing it as crosses. So this is our external magnetic field over here. Okay, and then in this magnetic field, I'm going to place our current carrying wire. So I will take that same current carrying wire and put it in this magnetic field over here. So that's our current carrying wire. Okay, Now, what this current carrying wire will do, it will set up its own magnetic field. And we know, we have seen earlier, that the magnetic field on the right hand side of this wire is shown as crosses. So I'm going to draw these magnetic field lines, the circular magnetic field lines of the current carrying wire as crosses on the right hand side. And then on the left hand side, these are dots. So I'm going to draw some dots to show the magnetic field lines set up by this current carrying wire. So we have two sets of magnetic fields. One is the external magnetic field shown by these green crosses, and the second is the magnetic field set up by the current in the wire, which is shown as the blue crosses and dots. Okay. Now these magnetic field lines are going to interact with each other. On the right hand side, we can see both magnetic field lines are pointing in the same direction, and therefore overall it increases the density of the magnetic field lines on the right hand side. So we have a much stronger magnetic field on this side due to the interaction between the two magnetic fields. On the other hand, if we consider the left hand side of the wire, then the two magnetic field lines are pointing in opposite direction. So therefore, they kind of cancel each other out slightly or make the magnetic field lines less dense on that side. And therefore, we end up with a much weaker magnetic field on this side of the wire. So we have one side where we have a stronger magnetic field, and then another side where we have weaker magnetic field. Okay, so because of this magnetic field being stronger on one side of the wire and weaker on the other side of the wire, overall there will be a force pushing the wire from the stronger magnetic field towards the weaker magnetic field. So on the wire there will be a force acting in this direction. And this is the electromagnetic force known as the Lorentz force acting on a current carrying wire placed in an external magnetic field. And this force is a result of the interaction between the two magnetic fields. Okay? Now, the magnitude of this Lorentz force, or basically the size of this Lorentz force, depends on, of course, in the external magnetic field, and it also depends on the current I through the wire. So we have a current I through the wire. Only when there is a current I, we will have this force acting on the wire. And it also depends on the length of the wire placed in the magnetic field. Now you have to be really careful about this L over here. So this wire can be longer and part of it could be outside the magnetic field as well, but only the part that is within the magnetic field is actually interacting with that external magnetic field, and therefore the length of the wire that is responsible for this Lorentz force is only this length over here. So this L, which is the length of the wire within the magnetic field, is what generates or what causes this force over here. So this F depends on that L, not the full length of the wire. If it's extended outside, we don't have to worry about that length. So remember, this L here is the length of wire in the magnetic field, because only that part of the wire is interacting with the external magnetic field, and therefore produces this Lorentz force. Okay, and it must be in meters, and this current I, of course, has to be in amps. The magnetic field strength, we know it's measured in Tesla, and this is the Lorentz force, so it has to be in newtons, because any force is measured in newtons. Okay, now we have seen how we get the direction of this Lorentz force due to the interaction between the two magnetic fields, but there is a slightly simpler way of getting the direction of this electromagnetic force as well, and we are going to look at that next. So this one, the direction of this Lorentz force is given by another right hand rule, and this one is called the right hand slap rule. Okay. Now, to apply this rule, what you need to do is you take your right hand and then point the fingers of your right hand in the direction of the magnetic field, and then point your thumb in the direction of the current. So this should be pointed in the direction of the current. The rest of the fingers should be pointing in the direction of the external magnetic field. And then the palm of your hand will be pointing in the direction of the Lorentz force. So if I take this right hand over here, then the palm is facing out of the surface. So therefore, the Lorentz force in this scenario will be pointing out of the surface as well, and that will be the direction of F. So I have shown it as a dot because we know we are trying to show a vector which is pointing out of the surface towards us, and that's why it should be drawn as a dot. Let me just clear this out a little bit. So this is our Lorentz force here pointing out of the plane. Okay. Now, if you apply this right hand slap rule to the scenario we have considered over here, then you have to take your right hand, point your fingers in the direction of the external magnetic field, which is pointing into the paper. So do that first, and then point your thumb in the direction of the current, and then you will notice that the palm of your right hand is facing to the left, which is the same direction as we have drawn over here. So the Lorentz force will be pointing to the left. So instead of using this interaction between the magnetic fields, we can simply use the right hand slap rule to get the direction of this Lorentz force as well. Now let me show you a quick example of what we have learned about current carrying wire placed in an external electromagnetic field by answering this past NCEA exam question about this topic. So what we have over here is Mary, Martha, and Luke are doing some experiment with wires and batteries, and they connect a long wire to a car battery and a switch and hold the wire as shown in the diagram. When Luke closes the switch, they notice that the wires move. Charge on an electron is given. Okay. And over here it says the diagram below shows the experiment looking down from above. So this diagram over here is basically showing you what the circuit looks like. It's a top-down view. You can see the battery and you can see the wires and the switch as well. Now, part A of the question asks you, referring to this diagram, determine the direction of the magnetic field at the point X. So this is the point X. We have to determine the direction of the magnetic field at that point due to the wire AB. So you have a current carrying wire. First of all, if we close the switch, the first thing we need to do is identify which direction the current will flow through wire AB. So we know that current always flows from the positive terminal of the battery through the wires back to the negative terminal of the battery. So this is the direction of the current in wire AB, and because of this current carrying wire, it will produce a magnetic field, those circular magnetic field lines, and we have to determine which direction the magnetic field will be due to this current carrying wire at this position. So don't worry about the second wire right now, but use your right hand grip rule. Point your thumb in the direction of the current in the AB wire, which is to the right, and then you can see your fingers are curling in a way that at position X, the circular magnetic field lines will be pointing out of the surface, which means it should be pointing towards you. So to show that as a vector, the magnetic field is basically, you can draw it as a dot, but what you have to do is choose from these following options. Is it out of the page? Is it into the page? Is it towards the top of the page, towards the bottom of the page, left or right? So the correct answer is basically out of the page. The magnetic field at position X, at point X, due to the current carrying wire AB, is out of the page. Now, because of that magnetic field, so this dot here is showing the direction of the magnetic field at this position. And along this entire wire, basically, there will be these magnetic fields due to the second wire. So you can see the CD wire is now placed on an external magnetic field. Now CD wire itself is carrying a current I in this direction here. So you end up with this CD current carrying wire placed in an external magnetic field, which is this magnetic field B is produced by the AB wire, and the magnetic field is pointing out of the page. So now to determine the direction of the Lorentz force acting on the CD wire as it's placed in an external magnetic field, we have to use our right hand slap rule. So now what we are going to do is point our fingers in the direction of the magnetic field, which is out of the page, and then point your thumb of your right hand to the left, because the current in CD wire is to the left, and you can see the palm is facing up, which means the Lorentz force acting on the CD wire due to this external magnetic field produced by AB wire is pointing up like this. So this is the direction of the Lorentz force. Okay, so direction of magnetic field at X is out of page, and direction of force on CD is towards the top of the page. So this one is towards the top of the page. So these are the options. Sorry, we don't have to circle it. We have to choose from these two options and then write the correct answer over here. So that was the first part of the question. And then the second part of the question, part B, is the length of the wire between Mary and Martha is 5 meters. The size of the force between the wires is this. So we are given here, that's our L, length of the wire. We are given the Lorentz force F acting on the wire, and the current in the wire is this. So that's our I. Okay. We have to calculate the size of the magnetic field at the point X and give the correct unit with your answer. So we have to use the Lorentz force formula, F equals to B I L, and then we are trying to solve for B, so we'll rearrange the formula, and then we get B is equals to, we will take this IL and then move it to the other side of the equation, so it becomes F over IL, because I and L are multiplied over here. So that gives us the force is 0.013 newtons. Divide that by the current, which is 35 amps, and then times the length of the wire, and everything is in correct unit, so we don't need to do any conversion. So if we do that, then what do we get? Okay, so we get 0.0040 zeros and then 7428. Okay, and that is B, magnetic field, so it should be in Tesla. And if we want to do the rounding properly, then basically all the numbers that are given to us are given up to two significant figures, so we can round this to the first two significant figures. These are all placeholders, so we have to keep all of that, and then we need two significant figures, so it should be 7 for Tesla rounded to two significant figure. So that's how we can use this formula, Lorentz force, to calculate this magnetic field strength. Okay. Okay, so let's now move on to the second topic, which is a charged particle moving in a magnetic field. Now, previously we have seen that we started with a uniform external magnetic field, and we are going to do the same over here. So our magnetic field, we are going to consider another magnetic field which is also pointing into the paper, and therefore I'm drawing it as crosses. And in this magnetic field, we are going to have a charged particle, a single charged particle, and we are going to consider a positively charged particle, and that is moving upwards with a velocity v. Now, you might remember that current is basically rate of flow of charges. So inside the wire, there are electrons that are flowing in the opposite direction. Similarly, a moving positive charge is just like a current. So this moving positive charge will produce its own magnetic field, just like a current carrying wire does. And then this magnetic field will interact with this external magnetic field B, and there will be a Lorentz force acting on this single positive moving charge as well, because a moving charge is just equivalent to a current. A positive moving charge is equivalent to a current, a negative moving charge is equivalent to a current in the opposite direction. Okay, so if we apply our right hand slap rule, then to do that, take your right hand, point your thumb this time in the direction of the velocity of this positive charge, which is basically the same as the current, and then point the rest of the fingers in the direction of the magnetic field, which is going into the paper. And then you will notice your palm is facing to the left, which means there will be a Lorentz force acting on this single charge particle, which is moving through a magnetic field to the left. So this is the Lorentz force. Just like we have Lorentz force acting on a current carrying wire, we also have a Lorentz force acting on a charged particle that is moving in a magnetic field. And this Lorentz force is equals to the strength of the magnetic field times the charge on this particle. So if the charge on this particle is Q, then that's what this force depends on. And it also depends on the velocity of this moving charge. So that's how we can calculate this Lorentz force over here. Okay, now one thing you have to be careful about, remember this velocity v that we are using in this formula over here has to be perpendicular to the magnetic field. Now we can have a scenario where the velocity is not exactly perpendicular to the magnetic field because of the way the charged particle is moving in that magnetic field. In that case, you have to apply your knowledge of vector, because velocity is a vector, and split the velocity into horizontal and into components which is parallel and perpendicular to the magnetic field. And only the component that is perpendicular to the magnetic field is what we use to calculate the Lorentz force. So if the velocity is parallel to the magnetic field, so if the charged particle is moving in the direction of the magnetic field, or if velocity is anti-parallel, that means it's moving opposite to the direction of the magnetic field, then there is no Lorentz force. So the Lorentz force will be equals to 0 Newton. So only if the charged particle is not moving in the direction of the magnetic field or in the opposite direction of the magnetic field, then there will be a Lorentz force. And to calculate the Lorentz force, we have to use this formula F equals to BQV. But remember, the V we should use in this formula is the velocity which is perpendicular to the magnetic field. Okay, so that gives us the magnitude of this Lorentz force. To get the direction of the Lorentz force, we have already seen how we used the right hand slap rule to determine that in this scenario the Lorentz force is to the left. Now, instead of a positive charge particle, if we have a negative charge particle, then what will happen is, so if I take the same magnetic field and then apply it to a scenario where instead of a positive charge, we have a negative charge, which is moving in the exact same direction with the velocity v, charge q, then whichever direction you get for the Lorentz force using your right hand slap rule, you have to reverse the direction of that force. So on a negative charge, the Lorentz force will be pointing to the right. Okay, but in both cases, you can see the Lorentz force and the velocity are perpendicular to each other. And because of that, the object, the charged particle, cannot keep moving straight. And what this force will do, it will change the direction of the velocity. The only thing it can change is the direction of the velocity, because it's perpendicular to the velocity. It cannot change its magnitude. So the charged particle cannot move straight through this magnetic field, and what it will do, it will start bending in this direction, and it will start following a circular trajectory, because we know that in a circular motion, the velocity and the centripetal force, they're always at 90 degree to each other. So what will happen over here, when the charged particle is over here, the velocity will be tangent to the circular motion, and the Lorentz force will be acting towards the center of the circle, and therefore that will become the centripetal force. Okay, same thing will happen to the negative charge. The negative charge, again, it cannot go straight. It will keep the magnitude of the velocity same, but it will change the direction, and the negative charge will also follow a circular trajectory, and it will keep changing the direction of the velocity. And at any given point, the Lorentz force will be always pointing towards the center. So when the charged particle is here, then the velocity is in this direction, tangent to the circle, and the Lorentz force is again perpendicular to the velocity, pointing towards the center of the circle. So any charged particle moving in in a magnet, in an external magnetic field, will always follow a circular trajectory. And the centripetal force, the required centripetal force to follow a circular trajectory in this case, is given by the Lorentz force, the electromagnetic force. Okay, we know the required centripetal force is mv square over r, and in this case, the centripetal force which is provided by the Lorentz force is bqv. So if you simplify this, you get mv, because one of the v cancels out from both sides, so this v cancels out one of the v from here, and we get mv over r is equals to b times q. Okay, so to get the different parameters of the circular trajectory of a charged particle moving in a magnetic field, we can use this relationship that the centripetal force here is provided by the Lorentz force, and then simplify it to get different quantities. So for example, if I want to work out the radius of the circular trajectory, then I can rearrange this formula, this relationship over here, and then solve for r. So if I want to solve for r, I have to swap these two, and I'll get mv over bq is equals to r. So that's how I can calculate the radius of this circular trajectory. It depends on the mass of the charged particle, velocity of the charged particle, the strength of the magnetic field, and the charge of the particle. Okay, and you can see this radius is proportional to the velocity. So if it's moving faster, then it will follow a trajectory with a bigger radius. That means it will be like a circular path with bigger r. And if it's moving slower, then it will follow a tighter circular trajectory, because it will have a smaller radius. Another important application of this charged particle moving in a magnetic field is a mass spectrometer. So, if we take the same magnetic field, we have a uniform magnetic field somewhere set up by some magnets, and then if you fire a bunch of different isotopes of the same element, but they're all ionized, so they all have same charges. Let's say they're all positively ionized, but they have slightly different masses from each other. So if you send these charged isotope particles into this magnetic field, so they will all enter the magnetic field at same velocity. They are fired at same velocity, but because they have different masses, you can see from here the mass and the radius, they're proportional to each other as well. So when they bend in the magnetic field, the more massive isotopes will bend less, so they will follow a trajectory which follows a much broader circular or wider circular track. Okay, on the other hand, if you have this isotope which has smaller mass, then it will follow a much tighter circular trajectory. So this will separate. So this isotope will end up coming out like this isotope will end up coming out like that. So depending on how many different streams of isotopes are coming out, we can identify how many different types of isotopes we have in that element. And then the lighter isotopes will bend more as they move through the magnetic field, and the heavier isotopes, more massive isotopes, will bend less. So that's how the radius and the mass, the relationship between the radius and the mass of the charged particle is used to separate these different isotopes of an element. Let's now quickly look at a past exam question about this topic. So we have an electron cutting the magnetic field that experiences a force which makes it follow a circular path, and the electron is traveling from left into the field. So two key things over here: one, it's an electron, so it's a negatively charged particle, and second, it's traveling from the left into the field, which means it's starting over here, that's our electron, and it's moving from left into the field. So that is specifying the direction of its velocity. So we know that its velocity is to the right. Okay, and what we have to do is we have to clearly mark on the diagram the direction the electron moves around the circle. So basically what we need to do is identify or figure out which direction the Lorentz force is pushing this electron, and then based on that Lorentz force it will either bend this way or it will bend this way. So Lorentz force will be either pushing it down or up. So that's the thing we need to figure out first, and once we figure that out we will easily identify, is it going to go on a clockwise circle or is it going to move anti-clockwise. Okay, so let's try to do that first. So what we have is the velocity is to the right, the magnetic field B as shown by the dots is pointing out of the paper. So let's use our right hand slap rule, point our thumb in the direction of the velocity, which is to the right, point our rest of the fingers out of the paper in the direction of the magnetic field, and you will notice that the Lorentz force is pushing it down. Okay, but remember it's an electron, so if the right hand rule gives us a Lorentz force downwards, then for an electron the Lorentz force is actually upwards. So this will be the direction of the Lorentz force once it enters the electric field. So I think it's better to draw, once the electron is here, then the Lorentz force will be pushing it upwards. Okay, and because of that reason it cannot follow a trajectory go straight, but it will bend in this direction. So an electron will curve like this. So that means this electron that the circular trajectory is shown over here will follow a circular trajectory in the anti-clockwise direction like this. Okay, how did we figure that out? Just by looking at the direction of the Lorentz force acting on this electron, and we can see that it bends like this. So it is following a circular trajectory which is going in the anti-clockwise direction. Okay, and for the second part we have to use physics principles to explain why there is a force on the electron as it cuts the magnetic field. Now remember, the source of this Lorentz force is due to the interaction between two magnetic fields. One is the original magnetic field, the external magnetic field B that is shown by the dots, and number two is the magnetic field produced by a moving charge, which is equivalent to a current, and we know that a current produces a magnetic field. And because of the interaction between these two magnetic fields, there will be a region where the magnetic fields add up because the two fields are pointing in the same direction, making a stronger magnetic field. And then there will be another region where the two magnetic fields point in the opposite direction, making it weaker over there. Okay, and due to this difference between the strength of the magnetic field in these two regions, which arises because of the interaction between the two magnetic fields, there will be a Lorentz force pointing from the weaker magnetic field, sorry, the stronger magnetic field area to the weaker magnetic field area. And that is the origin of this Lorentz force. Okay, so in your answer, that's what you have to explain. So I have covered the first two topics, this one over here and this one over here. in this video, and I think it's a good time for me to stop. And what I'm going to do is basically explain the third topic and some application, which is basically the fourth part, in another video, so in a separate video. So keep an eye on the channel. See you guys next time.